Much. First of all, let me thank the organizers for inviting me to this very wonderful conference. I enjoyed all these talks very much. So the talk is about spectral periodicity of spinon continuum in the U1 quantum spin liquid of spin ice type. So I would like to thank the discussion with Jeff and Michelle for comments. So this is some little small work from my group in recent years on this spin ice, in the context of spin ice. So today I will just talk about the last one, which is on archive two months ago. So let me start from a very famous experiment in the fraction quantum Hall effect. This is slightly deviated from the topic. So this is a very famous experiment called short noise measurement. So they measure the short noise of some cloning current. They find they confirm the existence of a fractional charge, the Laughlin quasi-particle. So this is a very famous experiment, and it can confirm the charge fractionalization in fraction quantum Hall effect. So fraction quantum Hall effect is arguably the only existing topological order so far in nature. So fraction quantum Hall effect or Laughlin state is an example of chiral abelian topological order. So chiral abelian topological order implies fractionalization, implies fractionalized and deconfined excitation, and it's described by Chen-Simon gauge theory. So these if we impose the charge conservation, which is the case for fraction quantum Hall effect, so these fractional excitation will carry fractional charge. So with this charge conservation, we have fractional charge excitation. So symmetry, which is the U1 charge conservation, makes the topological order more visible in experiment. Without this global charge conservation, you won't see a fractional charge. So charge makes this topological order more visible in experiment. This is the message I want to deliver. So U1 quantum spin liquid of spin ice type is like a topological order, is very much like a topological order. So the question I'm going to answer is, what is the sharp physical observable to observe for U1 quantum spin liquid of spin ice type? These are theoretical results from very early days. So in quantum spin ice U1 quantum spin liquid, there are deconfined spinon excitations. They are deconfined magnetic monopole excitation. There are gapless gauge photons. And this gapless gauge photon is due to a homogeneous U1 gauge structure and is protected by the gauge structure. So we need to confirm all these three excitations if we want to confirm U1 quantum spin liquid. Clearly, there is a large energy separation between gauge photon and spinons. So gauge photon is a very, very low energy excitation. Considering the fact that rare earths interacting with very low energy super exchange interaction, so this to observe this gapless gauge photon is very hard. Moreover, there is a technical issue that this spectral weight, spectral intensity is suppressed as function of energy. So even if one can see this kind of dispersion, in the end it's more like a pseudo gap behavior. So this is very hard, right? This is very low energy scales and suppressed intensity. But there is also another very interesting prediction by Savarian balance saying the heat capacity, the T cube, the heat capacity due to gapless gauge photon can be 1,000 times larger than the photons. So that I would regard as a sharp prediction. So today I will try to give another answer. What's the sharp observable to confirm U1 quantum spin liquid? So the answer is the spectral periodicity of the spinon continuum. So these are one U1 quantum spin, the other. So I put a 0 and pi. I will explain later why it's 0 and pi. In this pi case, the spectrum has an enlarged. This is spinon continuum. So this is momentum. This is energy. So there is the enlarged periodicity, the enlarged spectral periodicity. So the enlarged spectral periodicity is very much like a fractional charge in fractional quantum Hall effect. Yeah. So let me start from some realistic models. In fact, in the first day, Jeff told us there are actually two realistic models. One is this this very beautiful model. So describe usual Kramers doublet and a non-Kramers doublet has been studied by these people. And my student and also this Mike Herman's student And my company, we introduced a new model for this dipole octuple doublet. Yeah. To capture the physics, to capture the universal physics, we don't need to work on these more realistic models. We can just work on some more parent simplified models, just as Nick Shannon was saying yesterday. We can work on simplified models. So here I'm just focused on the XZ model to deliver the universal physics. So the physics I'm talking about is universal. It's independent from the model I'm working on. So the first diagram of this model has been studied by various people. And so when this transverse coupling is not very large, transverse coupling is, if the sign of this is positive, there is no sign problem. We can study it more systematically. So when this transverse coupling is weak, we are in this U1 quantum spin liquid regime. There is a deconfined spinons with emergent gauge photons. And when this is large, you get magnetic order. How about the other side? When this sign of this J-perp is negative. So there are two prior studies. So in the very early study by my company and collaborators, so they argue perturbatively that in this regime, when the J-perp is less than 0, this U1 quantum spin liquid can be related to the U1 quantum spin liquid on the right by unitary transformation. So then both sides will be a U1 quantum spin liquid. So this is the perturbative argument provided by these people. And more recently, maybe 5 years ago, so my academic assistant Songbin Li and the collaborators, they studied this side, so-called frustrated side, when this J-perp is less than 0, such that this coupling is antiferromagnetic and frustrated. So they point out, so they call this pi flux. Okay, this very pi flux state. So they point out due to some spinon, low energy spinon excitation, so the regime of this U1 quantum spin liquid is the stability of this U1 quantum spin liquid is greatly enhanced. Yeah. So this is very good. It tells us this U1 quantum spin liquid is more robust against the perturbation than this U1 quantum spin liquid. So this is the stability property of this U1 quantum spin liquid. What I'm going to talk about it today is telling people that this side has a very important property, has not been noticed before. By the way, this is a more recent work by Nick Shannon. He found 3 classical spin liquids on the right hand side, on the left hand side of this Phys diagram. So let me return to my talk. So besides the quantitative difference of first stability of this side and this side, there will be some very sharp distinction between this U1 pi spin liquid and U1 0 spin liquid. So what's the sharp distinction? So let me start from this perturbation theory. So this is the original XZ model. If we do it in a third order perturbation theory that has been explained by Yongbae Kim in the first day. So this is just doing third order perturbation theory and find out the flippable plaquette on the pyrochlore lattice. You can obtain a ring exchange, and if you do a lattice gauge theory mapping, you can define E field as SD and the vector gauge potential as S plus minus operator. In the end, you obtain a lattice gauge theory on dual diameter lattice formed by the center of the tetrahedrons. So you get some kind of lattice gauge theory defined on the diameter lattice. And this coupling K is basically the ring exchange, and this ring exchange becomes this cosine curl A. So then when the sign of that is negative, you favor there is a background pi flux over here. If the sign of that is positive, you get a 0 flux. So the pi flux is essentially, so if you this pi flux is important. If you transport this spinon, a topological defect of this spin-ice manifold around this parallel diagram defined by this translation operator. So there are different translation operators. If you translate it like this, you'll find the flux, the normal bond flux experienced by spinons is identical to the flux trapped by the buckled hexagon. So this is very important. Realize that means if you have pi flux, the translation of spinons along two lattice spacings, two lattice vectors will be anti-commute. So this is important. This is mathematics, right? So the physical consequence is that when this two translation operator for this spinon degrees of freedom anti-commute, that will lead to a spectral intensity enhancement. So this is some mathematical proof. Let me just jump through the result. So the claim is that when there is a pi background flux, there will be a spectral intensity enhancement. So the spectral intensity periodicity can be reflected in the spectral intensity and the lower excitation edge or upper excitation edge of the spinon continuum. And so there is the enhanced, so the spectral intensity will be the half of the reciprocal lattice vector instead of the integer monopoles of reciprocal lattice vector. But if you do an elastic measurement, if you don't measure the dynamic, if you measure the statics, if you measure the elastic measurement, you won't see any actual Bragg peaks. So in a dynamic measurement, you would see as if the system breaks translational symmetry. But if you measure statics, you don't see any symmetry breaking. So this is very sharp. So we actually did some calculation to demonstrate the bar prediction. So when this sign of J-perp is greater than 0, which is unfluctuated, and there's only zero flux, you don't see enhanced periodicity. The periodicity is defined by the reciprocal lattice vector, which is this vector and this vector. This point and this point and this point are equivalent. The spectral intensity is identical. But if you have the pi flux, U1 pi, when this sign is negative, then you would have enhanced spectral periodicity. So here, this spot will be equivalent to this spot, and this spot will be equivalent to this spot. So the low excitation will have this spectral intensity enhancement. Let me conclude. So for U1 pi quantum spin liquid, we have enhanced the spectral intensity, and this can be immediately confirmed by inelastic neutron scattering. So there's a couple of predictions. So for usual Karamas doublet, and spinon continuum can be immediately detectable by inelastic neutron scattering. And so I asked Lucia and Kate that this turbulent tangent actually is not in the pi flux state. It's proximal to zero flux state. So you wouldn't see any features in this material. Yeah. So for non-Karamas doublet, so spinon continuum cannot be detected by inelastic neutron scattering, but the proximate magnetic order or proximate quadrupolar order would break translational symmetry due to the presence of this background pi flux. So this can be detected. The proximate magnetic order, proximate quadrupolar order for non-Karamas doublet would break translational symmetry. So that would be a sharp prediction. So the early work by Song-Min Lee and Onoda and Balance, they point out pi flux state. This pi flux state is more robust against the perturbation. So that's great. That means for a real material, for a candidate material, is more likely to be in the pi flux state. So then it's more likely to have this spectral intensity enhancement. So I hope eventually there will be a Karamas doublet material that has this spectral intensity enhancement. And that's a very sharp feature because also spinon excitation is a higher energy excitation than the photon degrees of freedom. So that means it's easier to detect experimentally. In terms of energy resolution, it's easier to detect experimentally. So by that, thanks for your attention. Yeah.
Thank you very much. Yixi, Colin, and Bruce.
I'm just a little confused about, okay, you mentioned this enhancement is a spectral periodicity. It's not a spectral weight, yes? I just want to ask. It's like you have like a resonant enhancement model where simply you have just a new periodicity you can observe?
You have so if you imagine you do a inelastic neutron scattering measurement, you measure some spectral intensity with a function of momentum, with momentum if you fix your energy, okay, with their momentum. So if you translate these spectral intensity by half the reciprocal lattice vector, you will find that the spectral intensity stays the same. But in the conventional case, it's not. In the conventional case, the spectral intensity is defined by, spectral periodicity is defined by integer multiples of reciprocal lattice vector. So now it's half. So that's as if the symmetry is broken. If you break the translational symmetry by enlarging the unit cell, your branch zone is reduced to be half of the original branch zone. So then you will have this enhanced spectral periodicity. But because this is this is very much like a topological phase, there is a fractionalization going on. So the spinon experiences the background pi flux. So it's as if the branch zone is being reduced. So you have this spectral enhancement in the spinon continuum, but not in the statics, only in the dynamics. You will see this enhancement of spectral intensity, spectral periodicity.
And that's a proper gauge invariant structure factor you have here? It's not, the gauge is not fixed, right? It's gauge invariant.
Yeah, this observable is all gauge invariant. Yeah, sure. Yes. The physical observable is gauge invariant. Yeah.
And that's what you computed?
Right, yes.
Colin.
I just wanted to check one thing, which is I'm aware that if you enlarge the unit cell, the gradient zone will shrink, and all the dispersion relations will now have this double periodicity, if you will, dispersion relations. But in many cases, the intensities actually don't have all of that structure in it. They're not fully doubled like that. And so I wanted to ask, in your calculations, are you talking about the dispersion relation acquiring this reduced zone, or are you actually talking about the full intensities?
I think it's the full. So the spectral periodicity can be reflected in spectral intensity, the lower exciting edge and the upper exciting edge. So the intensity at some particular momentum and energy will be identical if you translate this momentum by 2 pi 110. For FCC that is, the periodicity is 4 pi. So this is 2 pi, the half of that. So you just translate it by this momentum and this momentum. This spectral intensity stay invariant. Yeah.
Bruce?
So you mentioned that Lucille and Kate had determined that ytterbium titanate is approximate zero flux.
Yeah.
So what's that on the basis on? Is that simply the form of the microscopic Hamiltonian, or is it?
Yeah. So I checked with Lucille. I asked for the sign of this term. Right. He told me this is positive. So then it's a zero flux. So then ask Kate. So you guys have this experiment many years ago. You actually compare. You did this comparison. You compare the spectral intensity at this momentum and off by 2 pi 110, and it's different. Yeah. If we do the same, that would be great. You discover ion quantum spin liquid. Yeah.
But this calculation does not take into account some kind of form factor. So the actual scattering intensity may not be exactly like that. So this is really just, in the end, it's really just a dispersion relation.
This is theoretical calculation.
Yeah,
I mean, experimentally, then some other things enter.
Right, but the actual scattering cross-section may not exactly like this.
Yeah, well, at a minimum, you'd have to add the form factor.
Right,
Yeah.
But the atomic form factor is considered kind of a trivial thing, but I'm talking about the conversion from some sort of theoretical variables into actual spin operators. Usually you pick up a magnetic dependence on that you might call the structure factor, and that would not have been enlarged periodicity.
Any question?
Yeah, I have one technical question. So in principle, in order to see all these structures, you have to look at this PSG analysis, projective symmetry group analysis. And this is some, I assume this spirality belongs to some particular PSG class. Right?
Yeah, this is U1B.
Sorry,
This is U1B, yeah.
So is this really the only choice?
Yeah, I'll try to use less, theoretical notation. This is just a U1B. So this symmetry fractionalization occur in the translational symmetry. So any, this is a three-dimensional lattice. So there are three lattice vectors. Any translation, any two translation of any out of these three will be anti-commute for these spinon translations. So that's just the U1B states. U1B state for the translation symmetry.
So you can have different kinds of spectral even for the opposite side.
Well, are you saying if I impose further symmetries, then will be a finer, yeah. Right. So that's a great question. So yeah, so if you impose further symmetries, there will be a finer classification. So that means your spectrum will have more properties. So then, that's a very important question. Like, and more generally, how do you detect topological order in experiment? And if you're given some particular lattice symmetries, then you figure out these symmetries and ask, how do I manipulate the spectrum, or how do I manipulate the experimental data to manifest these symmetry fractionalization? Yeah, that's a very important question. That if you know that, so if you know these, I think this requires knowledge of this final classification. Then you figure out how this spectrum works out under these particular symmetries. Then you design some method to reveal this particular property. Because this requires, for instance, integral of integration of some spectral intensity across some momentum, along one momentum, trace out a particular momentum, and then you get to reduce the spectral intensity, and then you're doing some particular treatment. For instance, some mirror symmetry, there will be some very special recipe to do this. Yeah, we can talk about this later, but this is a very important question. Yeah. Yeah.
Okay, so if not, so the question is, let's thank again for a very interesting talk.